Hello, in this video we're going to go over evaluation of this double sum. This is a problem that was suggested to me by one of the users on my channel. Okay, so here is the problem. The sum r equals 0 to n, sum k equals 0 to r, negative 1 to the power of k, k plus 1 times k plus 2 times n plus 5, choose r minus k. You may want to pause the video, think about this problem, and then come back and see how I solve the problem. Keep in mind that this is not an easy problem. Okay, so let's start with calling this sum an. So this is what I started doing. So r equals 0 to n, k equals 0 to r, negative 1 to the power of k, k plus 1, k plus 2, n plus 5, choose r minus k. So the idea that I had was to try to come up with a recursion for an. So what I did was I replaced n by n plus 1, and the only term that changes is that term. So an plus 1 becomes the sum r0 to n plus 1, sum k equals 0 to r, negative 1 to the power of k, k plus 1, k plus 2, n plus 6, choose r minus k. Okay, so now how do we relate binomials to the previous binomials? Well, that's the Pascal's identity that we can use to relate. So if you look at n choose I, that's equal to n minus 1 choose I plus n minus 1 choose I minus 1. That's the Pascal's identity. You can either prove that by algebra, or you can observe that combinatorially. Now, I'm going to replace this one by, so n plus 6 choose r minus k, by n plus 5 choose r minus k plus n plus 5 choose r minus k minus 1. Okay, if we do that, then we're going to get an plus 1 equals the sum r equals 0 to n plus 1, the sum k equals 0 to r, negative 1 to the power of k, k plus 1, k plus 2, n plus 5, choose r minus k, plus n plus 5, choose r minus k minus 1. So first of all, if you rewrite that from r equals 0 to n, and then sum k equals 0 to r, negative 1 to the power of k, k plus 1, k plus 2, and if we look at the first one, we get n plus 5, choose r minus k. So this is exactly an. If we look at this portion, there's going to be one more term left from here, which is the last term. I'm going to write that down for n plus 1. So if r is n plus 1, then I would get the sum k equals 0 to n plus 1, negative 1 to the power of k, k plus 1, k plus 2, n plus 5, choose r minus k. So that is when r is equal to n plus 1, and by the way, this is going to be n plus 1 minus k, because r is n plus 1. So this is the case when r is n plus 1, and this is the case when r is n. And I'm only going to do this portion for now. Let's look at the next one. For the next portion, r minus k minus 1, if you substitute r equals 0, that's negative. So we can just drop the r equals 0. So we could just say plus the sum r equals 1 to n plus 1, negative 1, and then the sum k equals 0 to r, negative 1 to the power of k, k plus 1, k plus 2, and then we have n plus 5, choose r minus k minus 1. And the reason is if r is equal to 0, this quantity is going to be negative, so we can just drop that term, and the rest of the terms give us this sum. Now let's look at what we get in the beginning. So this term right here, this is exactly an. So I'm going to substitute that by an plus the term right here. If you change r to if you change the range of r from 0 to n, and change this one from k equals, so if k is equal to r, this is also negative. So I can start k equals 0 to r, in fact, because I'm changing, I'm replacing r by r minus 1. R minus 1 goes from 0 to n plus 1. So now this becomes negative 1 to the power of k, k plus 1, k plus 2, and then n plus 5 choose. So this would be r minus k. Okay, so this is the second term, and then I'm going to keep the middle term. So I'm going to rewrite that as the sum k equals 0 to n plus 1. I'm basically going to keep that as it is, negative 1 to the power of k, k plus 1 times k plus 2, and then I have n plus 5 choose n plus 1 minus k. Okay, so as we see, this is going to be an. So what I got is this: an plus 1 is equal to 2an plus the sum k equals 0 to n plus 1, negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose n plus 1 minus k. Okay, so that's nice. I was able to reduce this sum, a double sum, to a single sum. So let's call this one bn. Okay, so this is good. So this is good progress, but we haven't been able to solve the problem yet because we haven't able to evaluate that sum. So let's evaluate bn plus 1 and see what we get. This is the sum k equals 0. So if you plug in n plus 1 for n, we get k equals 0 to n plus 2, negative 1 to the power of k, k plus 1, k plus 2, n plus 6, choose n plus 2 minus k. Okay, so let's see what we get here. If we use again the Pascal's identity, k equals 0 to n plus 1, negative 1 to the power of k, k plus 1, k plus 2. So we're going to use Pascal's identity. That would give us n plus 5, n plus 2 minus k, plus n plus 5, n plus 1 minus k. Now, for simplicity, let's actually substitute this one by n plus 5 choose k plus 4. These are the same thing because n choose I and n choose n minus I are the same. And this is just n plus 6 choose k plus 4. Okay, so that makes things a little bit simpler. I don't have to write down the negation here. So this is going to be n plus 5 choose k plus 3, and this is n plus 5 choose k plus 4. Now if you distribute this one, you're going to end up getting sum k equals 0 to n plus 2, negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose k plus 3, and then plus, okay, so now if you look at this sum, when k is equal to 0 and when k is equal to n plus 2, those completely make sense. But if you look at the second sum, when k is equal to n plus 2, if you plug in n plus 2 here, that becomes negative. So that's just 0. We can drop that term. So we can write this down as k equals 0 to n plus 1, negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose k plus 4. Okay, so now let's see if we can relate this one with what we already had. So we're gonna okay, so we're gonna see what this gives us. So going back and looking at what bn is, so bn is 0 to k n plus 1, negative 1 to the power of k, k plus 1, k plus 2, n plus 5, choose k plus 4. So n plus 5 choose k plus 4. So this guy is exactly bn. So I'm going to write that down as bn plus, and then the other guy, the sum negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose k plus 3. And this is k equals 0 to n plus 2. Okay, so this is what we get. And I'm going to call this one now a new sequence cn. So this seems like a little bit getting too complicated, but in fact we are getting things to be a little bit simpler. Each time we're making it simpler. So let's look at Cn plus 1 and see what we get. Cn plus 1 is going to be the sum k equals 0 to n plus 3, negative 1 to the power of k, k plus 1, k plus 2, and I'm going to use the identity again, Pascal's identity. That would be, it would turn out to be n plus 6 choose k plus 3, which I can turn that into n plus 5 choose k plus 3 plus n plus 5 choose k plus 2. So if I do that, I would get the sum k equals 0 to n plus 3. Now, if k is equal to n plus 3 here, this would give us n plus 6. N plus 6, 5 choose n plus 6, that's just 0. So I can just do n plus 2. Negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose k plus 3. So if you think about this one, this is exactly Cn. This is precisely Cn plus the next sum is k equals 0 to n plus 3. So both of them make sense. K equals 0 is valid. K equals n plus 3 is also non-zero. So we can just, we're going to have to keep all of the terms. And let me put that in the next line. So this would be plus the sum k equals 0 to n plus 3, negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose k plus 2, I believe. Okay. So this is now what we're going to have to evaluate. So now this is a bit easier to evaluate. If you think about this one, this is like differentiating binomial twice. So how so? We're going to write down x plus 1 to the power of n plus 5. This is going to be the sum n plus 5 choose k, k equals 0 to n plus 5, x to the power of k. Now let's differentiate this twice. So if you differentiate this twice, you get n plus 5 times n plus 4 times x plus 1 to the power of n plus 3 equals the sum. So the very first term is a constant. The next term is a linear term. So we can start from 2 to n plus 5. K times k minus 1, n plus 5 choose k. Okay, so this is like really the same thing, because if you change the variable and if you replace k by basically k plus 2, you start from 0 to n plus 3. And then I have a term x to the power of k minus 1 here, k minus 2. Then you have k, so if k is equal to 0, you would have to get 2. So it would have to be k plus 2 times k plus 1, n plus 5 choose k plus 2, x to the power of k. So this is going to be equal to that. So now we're going to replace x by negative 1. And if we do that, we get 0 on the left. This side is going to be 0. On the right, we get the sum k equals 0 to n plus 3. So I'm going to first replace this one by negative 1, put it up front, then k plus 1, and then k plus 2 to make it similar to what I had up there. And if you look at this one and compare it with Cn, compare it with this term right here, it is exactly the same thing. So this is 0. So this means, so what does that mean? If we go back and look at Cn, this term right here ended up being 0. So what does that tell us about Cn? It means Cn plus 1 is equal to Cn, which means Cn is constant. Okay, so now let's just see what Cn was. If we rewrite Cn, Cn was this sum from 0 to n plus 2, the sum k equals 0 to n plus 2, negative 1 to the power of k, k plus 1, k plus 2, n plus 5 choose k plus 3, I believe. Let me go double check that. Yeah, so this is what we get. We know this is a constant, so let's just plug in n equals 0. So if we plug in n equals 0, we are going to get the sum k equals 0 to 2, negative 1 to the power of k, k plus 1, k plus 2, 5, choose 3. So all of these c's must be the same as c0. This is c0. So that tells us c0 is equal to, if you plug in k equals 0, we get negative 1 to the power of 0, 0 plus 1, 0 plus 2, 5, choose 3, which is 10, plus negative 1, 1 plus 1, 1 plus 2, 5, choose, I'm sorry, this is k plus 3. So this is 5, choose 4, and then plus negative 1 squared, 2 plus 1, 2 plus 2, 5, choose 5. Okay, so this is 1, this is 1, this is 2, this is 10, this is 20, minus 2, 3, that's 6, times 5, that's 30, plus 3 times 4 times 1, that gives us 12, so that becomes 2. So that tells us that Cn is exactly 2. Okay, so we're going to kind of work backwards and find Bn now. Now if we look at Bn, the recursion that we got for Bn was this. We got Bn plus 1 is equal to Bn plus Cn. So what does that tell us? It means Bn plus 1 is Bn plus 2. In other words, Bn is an arithmetic sequence. So Bn would be 2n plus B0. So every time you're adding 2 to the previous step. So now we're going to have to find B0. So if we go back and look at B0, we had B0 here. 0 to n plus 1, negative 1 to the power of k, k plus 1, k plus 2, n plus 5, choose k plus 4. So k equals 0 to n plus 1, negative 1 to the power of k, k plus 1, k plus 2. This is Bn. And then n plus 5, choose k plus 4. If we plug in 0 for n, we're going to get sum k equals 0 to 1, negative 1 to the power of k, k plus 1, k plus 2, 5, choose k plus 4. So this gives us, if you look at 0, we get 1 times 2 times 5, choose 4, minus, if we plug in 1, we get 2 times 3, 5, choose 5. 2 times 5 is 10, minus 6, that is 4. So that tells us Bn is equal to 2n plus 4. So this is Bn. Okay, so that's nice. We were able to find Bn, and the final step is to find An. So the recursion that we had was An plus 1 is equal to 2An plus Bn. This is what we got. So that tells us An plus 1 is equal to 2An plus 2n plus 4. Okay, so this is a little bit more complicated. I have a video on how to solve these linear recursions that I'm going to put the link in the post description of this video. So make sure to check that out, because that's the method I'm going to be using in order to solve this recursion. So the steps in solving this recursion would be twofold. First, we're going to have to look at the homogeneous recursion, which is xn plus 1 equals 2xn. So the way we do that is usually you look at the characteristic polynomial, but in this case it's just a geometric sequence. So it would be xn equals 2 to the n times x0. And second, we'll have to find a particular solution by guessing. So let's say you're trying to solve xn plus 1 equals 2xn plus 2n plus 1, and you want to find just one particular solution. So we're going to guess that xn is an plus b. We are going to substitute. We're going to get a times n plus 1 plus b equals 2 times an plus b plus 2n plus 4. Now we're going to compare the coefficients of n and the constant terms on the two sides. Coefficient of n on the left is a, coefficient of n on the right is 2a plus 2. Constant term on the left is a plus b, constant on the right is 2b plus 4. Let's solve this one. We get a equals negative 2, And if you plug that in here, we would get b is equal to -6. Okay, so what does that tell us? It means -2n minus 6 is a particular solution, which means just a solution to the recursion that we found, to this star. Now, how do we find all solutions? We add a particular solution to the solution to the homogeneous recursion. So we have 2an plus 2n plus 4. So all solutions would be a solution to the homogeneous, which is sum x0 to the power of n, and then minus 2n minus 6. Now, all we got to do in order to find an is to find a0. So let's find a0. So a0, by what we did before, is going to be, so we're just going to have to plug in 0 for n and see what we get. It's the sum from 0 to 0. So it's the sum r equals 0 to 0, sum k equals 0 to r, -1 to the power of k, k plus 1, k plus 2, n plus 5, choose r minus k, if I remember correctly. So let me double check. Yeah, so that's what we get. So now we are going to just evaluate that. That's very easy to evaluate. If we plug in r equals 0, k would have to be 0 as well. We get -1 to the power of 0, 0 plus 1, and this is going to be 0 plus 5, 0 plus 2, and then 5, choose 0. And that ends up being 2. Now, if we plug in n equals 0, we get a0 equals x0 times 2 to the 0 minus 2 times 0 minus 6, which is x0 minus 6, and this would have to be 2, which means x0 is 8. So that tells us that an is 2 to the power of n plus 3 minus 2n minus 6, and that is the final answer to the problem. If you have a different solution to this problem, put it in the comment section of the video. I will see you in the next video.